So let's do a lesson about nuclear decay. So curriculum stuff, you need to write nuclear equations using isotope notation. So that's the way that we, it's an A. That's the way that we wrote it yesterday. So we need to know alpha, beta negative, beta positive, and neutrino and antineutrino. So those are terms that you need to know. Predict the penetrating characteristics of decay products and use the law of conservation of charge and the law of conservation of mass to predict the number of particles. So these are physics principles right here. So we'll talk about how we use those physics principles properly. So the nucleus contains protons. The more protons it has, the more unstable the atom is. Why would that be? Well, we know that positives repel positives. So if you stick a whole bunch of positives in there, they're going to repel each other. The more positives, the more repulsion. That's why. So what do you notice happens to the number of neutrons in a nucleus as the number of protons increases, right? We can take a look on our data book. Right, so if we have carbon, right, it's got a mass of 12 on average, right? 6 protons, 6 neutrons. Fluorine, 9 protons, 10 neutrons, right? Neon, 10 protons, 10 neutrons. So pretty equal amounts of protons and neutrons. But if we look at heavier elements like uranium, so the most common is 238. So if we have a mass of 238 and 92 protons, that means we have 146 neutrons, right? Same with here, if we look at gold, right? Gold has 79 protons and 196, or 197, I guess would be the most common. So that would give us 118. So as we get bigger and bigger atoms, more and more protons together, we have more neutrons. And the reason for that is those neutrons work as spacers. They sort of space everything apart because the further away things are, the positive charges are from each other, the less repulsive force it's going to be. So those neutrons work as spacers. To become more stable, an atom will naturally decay into another element through the process of nuclear decay. And left long enough, all atoms would decay into iron 56. Iron 56 is the most stable element, and everything tries to become iron 56. So smaller things than 26 try to become iron 56, and then bigger things in element number 26 try to become iron. So if you left the universe alone for trillions and trillions of years, everything would just become iron. So there's 4 natural forces. Gravitational force we studied in physics 20, right? Fg equals mg, we know all that stuff. Electromagnetic force, we learned in this, so we know about electric forces and magnetic forces. But these are 2 new forces that we're going to talk about. So strong nuclear force and weak nuclear force. We don't talk about very often because they only exist within the atom, right? They exist within the nucleus. So what the strong nuclear force does is it holds protons and neutrons together in the nucleus, so it binds the atom together. And right, if we have a whole bunch of protons, so if we have a couple protons, there's going to be an electrostatic force between them, Fe, shooting them. So we need some other force that's stronger than our electric force to bound it in, and that's that strong nuclear force which holds it together. Okay, so the strong nuclear force is very strong, but it's only limited to the radius of the nucleus, right? So if I'm here, then I'm going to experience that strong nuclear force. It's going to be super strong. It's going to hold things together. But as soon as I step out here, I experience almost no strong nuclear force, right? So it's limited to the range of that nucleus. The weak nuclear force holds individual protons and neutrons together, and yeah, this keeps protons as protons and neutrons as neutrons. Yeah, here I have a video. Let's check it out. So when a nucleus decays, it emits either particle or EMR. And when a new element is formed from another element through nuclear decay, it's called transmutation. During transmutations, the element undergoing the change, or the reactant we can think of it as, is called the parent element, and then the final element is produced a daughter element. So those are some terms that I'll use. So we have a radioactive element here, right? It's unstable, and it shoots off a particle, and it can shoot off some energy, and it can turn into something else. So the ability for nuclei to decay or change can be followed like chemical reactions. Like chemical reactions, we must balance the left and the right side of the equations, right? So this is what it would look like. We have to balance the top number, so right here, this is 226, and if we add both of these together, it is also 226. On this side of the arrow is 88, and if we add these together, it is 88 as well. So if you're balancing the top numbers, that's our mass, and we would use the law of conservation of nucleons, which is physics principle number 8. If we're balancing the bottom numbers, it has to do with protons and charge. We use the law of conservation of charge, which is physics principle number 7. Okay, gotta know that. The alpha particle consists of an electron-stripped helium nucleus with 2 protons and 2 neutrons. So if I could see an alpha particle, right, it would be 2 protons, 2 neutrons with no electrons because they're gone. And because it's missing those 2 electrons, it has a 2+ charge. High-speed alpha particles are usually emitted from the decay of unstable isotopes of heavier elements such as uranium. And the symbol for an alpha particle is, so there's 2 symbols. So sometimes we put it as like a fish, like this, and it's got a mass of 2, mass of 4, and a charge of 2, right? Mass of 4, charge of 2. Or because it's the same as helium, sometimes you'll see an alpha particle written like this as well. Both are correct, both will be used. You'll have to know what both of them mean. So let's do an example here. So many smoke detectors contain an isotope of, it looks like mercum-241, but it's actually americium. But for fun, I'm going to call it mercum-241. Alpha particles emitted during the decay of red, white, and blue mercum-241 ionized molecules in the air, allow an electric current to flow between 2 plates in the smoke detector. During a fire, smoke particles come between those 2 plates and interfere with the current, setting off the detector's alarm. So write the alpha decay equation for this. So there's a lot of information. This is actually how smoke detectors work. Some smoke detectors, they use radioactive decay. And what you start off with is you start off with americium. So we'll have to look on our periodic table here for americium because we're not really familiar with it. Here's americium, and it's number 95. Right, so that bottom number I would want to be 95, and it says it's a specific isotope of americium. That's 241. So that's my americium. So it undergoes alpha decay and shoots off an alpha particle. So I need to figure out what the daughter nucleus is going to be. Well, what's going to be left over? Well, if we want to have 241 on both sides, and I've already used 4 of them, if I go 241 minus 4, then that's going to be 237. Right? 237 plus 4 is 241. And then 95, and I've already used 2 of them, so this bottom number is 93. So then I can look back on my periodic table, look up what 93 is. That's neptunium, which is Np. And I have written out the alpha decay. That's it. Okay, so I want you guys to try one. Pause the video, try it on your own, see how it goes. Write out the nuclear equation for the alpha decay of thorium-230. Okay, so first thing you would do, find thorium on your periodic table. Right, so here thorium, it's element number 90. So you'd write out thorium, element number 90, 230. And if it undergoes alpha decay, this number is going to be 226, because 226 plus 4 is 230. This number is going to be 88. We have to look up what 88 is. So 88 here is radium, which is Ra. And that's how you rate the alpha decay. Easy peasy. Okay, beta decay. Beta particles are high-speed electrons emitted from radioactive isotopes. So beta decay, that's the symbol for beta decay, results from a neutron changing into a proton. So there's a couple symbols for beta particles. So because it's an electron, sometimes symbolized by that, and it's beta negative, so you might see that. Electrons don't have any mass when compared to protons, but they do have a charge of -1. So that's one way that you might see it for beta negative. And then the other way that we can see it is this symbol here. So it's kind of like a bee with a longer tail and a charge of -1 and a mass of 0. Okay, so you have to be familiar with both of those. So show a neutron turning into a proton. Okay. We can do that with beta negative decay. So a neutron has mass, but it has no charge. If it turns into a proton has 1 mass as well, but it does have a charge of 1. So if we want both sides to be equal, right? We have 1 on this side, we already have 1 on this side, we want the top number to be 0. If we want 0 on both sides, then this bottom number has to be -1, which is a beta particle. So a neutron turning into a proton will release an electron, or a beta particle. So we're going to practice some more beta when we do these radioactive decay series. So unstable isotopes undergo a series of transmutations from both alpha and beta decay before forming a stable isotope. So once they decay, they don't stop. They decay and they decay and they decay until eventually, in maybe millions of years, they might become iron, and that's when they actually stop. So uranium-238 undergoes 14 different transmutations before stopping at a stable isotope of lead-206. And it doesn't technically stop, it just stops for a really long time, so it stops for our lifetime. Okay, so we can write out this, and we can base it on this charge here. So this is one way of writing alpha decay, or a decay series. So if I undergo alpha decay, this is my protons, and this is my mass. So every time I undergo an alpha decay, I lose a mass of 4, right? So I go from 238 to 234, and then I lose 2 protons as well. So I go from 83 to 81, as opposed to a beta decay, right? A beta decay, my mass doesn't change, but I would increase my proton number because it's a -1. So it goes this way, and this one goes this way, like that. So this shows the whole decay series for uranium-238 turning into lead-206. So I'm going to go through it, and I'm going to write it out. Right? So here is where we start. 238 uranium is number 92. So that's where we start out. So that's the first one. Oops. There we go. Yeah, I'll have to write it out here. So uranium is number 92 and number 238. And because this happens, it means it undergoes an alpha decay. And when it undergoes that alpha decay, it's going to turn into 234 and 90. And if I look up what number 90 is, number 90 is thorium. So that's going to be my first stop. So that's number 1. So that's not going to be where it stops, right? My thorium 234 here, it undergoes a beta decay. It moves 1 spot over there. So when it undergoes that beta decay, it increases its proton number to 91. The mass stays the same. And if I look up what number 91 is, protactinium. Wonderful name. Going to be the name of my next kid. So protactinium is right there. And that's what we start with our next step. So 234, 91, PA. And we look on the chart, it looks like we undergo another beta decay. So I have 0, -1, and beta. And it's going to turn back into uranium, but a different isotope of uranium. It's uranium-234 now instead of 238. Okay. And then my next one, I start off with that 234. Whoops. Went down too low. 92. Uranium. And the next one it undergoes is alpha decay. So it undergoes 1, 2, 3, 4, 5 alpha decays before it gets here. So I have to do 5 alpha decays. So 4, 2, and it's going to be 230 and 90. And I turn into number 90 we know with thorium. So we start off with that thorium, 230 and 90. And it undergoes another alpha, 4 and 2. It's going to be 226 and 88. And I know 88, I forget, I think that's radon. 88, yeah, here's a radium. Ra is radium, not radon. Rn is radon. Radium is 88. And that's going to be my next stop. It undergoes another alpha decay. And 222 and 86. And I look up what 86 is. And that is radon. Those guys are tricky. Radon. So we've undergone 1, 2, 3. So we have 2 more. That's going to be 218. That's going to be 84. And number 84 is polonium. And then I do one more, so 218, 84. Polonium, that's a 4. And I turn into 214, 82. And number 82 is, wrong button. Number 82 is, where are you, 82? Lead. But we turned into the wrong lead, right? We want to turn into lead 206. So we still have a few decays, right? So you can see we're here at 214 and lead, so that's good. Ooh, I wrote this weird. My lead should be here. And then I also did an alpha decay. So my next one, I'm going to start with my lead 214. And I'm going to turn into an alpha particle. No, beta particle this time. Let me erase that. So you can see I undergo 2 beta decays. So now I have beta decay, 0, -1. So I'm going to turn into 214, but 83. We haven't used 83 yet. 83 is going to be bismuth, your favorite pink liquid. And then 10, I start off with my bismuth. I undergo another alpha or beta decay, and I turn into 84, which I have used before. That's my polonium, but this time I'm polonium 214. I was 218 before. And then my polonium 214 undergoes another alpha, which is, and then I turn into 210 and 82, and I've used 82. That's lead, so I'm still not at lead 206. And then 12 is going to be 210 and 82 and lead. And it looks like I go 1, 2 over. I go 2 more at beta decays. And I turn into 83 again, and 210, and 83 is my bismuth. So I'm just going to finish off up here. So my last 213, I have my 210 bismuth. I undergo, bismuth is 83. I undergo 1 more beta decay. and I turn into 21084, and 84 is that polonium again, and then my last stop, 210 polonium. I undergo one more beta or alpha, and I turn into 206 and 82, which is 206, 82 is lead. That's what we wanted to finish as. So those are the 14 decays that happen before that uranium-238 becomes stable enough and stays at lead-206 for a long period of time. Whew. You probably just fast forward this anyway. So the last type of decay that can happen is gamma decay. It gives off gamma rays. So gamma rays are not charged particles like alpha and beta rays are particles, but photons of high frequency light. They will not normally bend in an electric or magnetic field because only charged particles do. Light does not get bent by electric or magnetic fields. Because they are photons of light, emission of gamma ray does not cause the nucleus to undergo any transmutation because they don't have any mass, they don't have any charge. It just transitions from a higher energy state to a lower one. And gamma rays look like this, like that, right? They have zero mass, zero charge. Sometimes they'll look like this because of the font, but that's what they should look like. Show a gamma ray after an alpha decay of thorium-227. Okay, so my thorium, forget what thorium is. Thorium is number 90, and it's 227. So when it undergoes an alpha decay, it makes 223 and 88, and I remember him. He is radium. I'm going to double check just in case. Yes, radium. What happens is this radium is in an excited state. So what my radium does to de-excite is it'll emit one of these gammas, right? And all it does is it goes from an excited state to an unexcited state, because if it's 0, 0, and I want both sides to equal the same, right? We would just say unexcited. So it emits energy, it goes into an unexcited state, and that is pretty much it. So this next example here is like the second part of it. You might not have it in your notes because I added this after I printed it off. But we can model this excited state and this unexcited state the same as we can model those energy level diagrams when we talked about the Bohr atom, right? So these are different energy levels that the nucleus can be at. It can be at level N, level M, and level L, right? So this might be the excited state that we were talking about, and this is the unexcited state. So when it goes from an excited state to an unexcited state, it shoots off this photon, and this is of gamma frequency, right? This is, if you calculated the wavelength of this, let me just calculate the wavelength of this really quick. It's going to be a really, really tiny wavelength. Oops. So 3 times 10 to the 8 divided by 2 times 10 to the 20. Oh, 1 times 10 to the 20. Right? That's a really, really tiny wavelength. That's in the gamma spectrum, right? We're way smaller than visible light, which is 10 to the -7, right? So this is a gamma ray that's given off. So, well, what is this state here? Well, it's not that tough of a question, because all we need to do is we need to find the energy of this, and we can just use E equals HF, and we want to be in electron volts. So if we go 4.14 times 10 to the -15, and we multiply it by 1 times 10 to the 20, we get the energy difference to be 1, 2, 3, 4, 5, 6. So it ends up being 0.414 times 10 to the 6 electron volts, or 0.414 mega electron volts. right? And it looks like, so this number's bigger, and then it gets smaller, and then it gets smaller, so this is going to be a smaller number. So then all I need to do is take my 2.155, subtract my 0.414, because remember, they're all mega electron volts, so all times 10 to the 6. And I get this energy level is going to be at 1.741 mega electron volts. And that's the type of question you could be. But it's really no different than a Bohr atom style question. So yeah, not tough. Okay, so gamma rays are the highest frequency of the electromagnetic spectrum. So you can see that last example that we did was times 10 to the 20, which is right about there in that gamma part of the spectrum. So the gamma ray photon is most energetic, even more energetic than X-rays. Alpha, beta, and gamma radiation all can be ranked based on their penetrating ability. So if we take a look at, here's a ray of beta particles in the middle. These are beta, these are alpha, and then these are gamma right here. So the alpha comes off the radioactive source, bam, it's stopped by a piece of paper. So it doesn't take much to stop an alpha particle, right? And then beta can travel through the paper, but if we have a little bit of aluminum, thick aluminum here, it's stopped by that. The gamma would go through the paper, through the aluminum, and we'd need several inches thick of concrete or several centimeter thick of concrete to actually stop it. Okay, so why do you think alpha is the worst, right? Well, alpha, we know, has a charge of +2. And it's quite a big particle. So it's got a big charge, and it's a big particle. An electron, right, is much, 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 much tinier. So this is a small particle, and it's got even less charge, right? So when you have a big charge, it's going to interact with protons and electrons in the thing that we're passing it through, so it's more likely to interact, right? And if you're bigger, it's going to be hard to go through the spaces between the nuclei. But an electron is much smaller, less of a charge, right? And if we're talking about gamma, a gamma photon, well, it has no charge, right? It has, how big is it? Well, I don't know, it's light, right? It's energy, it doesn't really take up anything, so that's why it's so much easier to pass through and less likely to interact with the matter inside of there. So that's why it's able to pass through. So ability to ionize and ability to penetrate, we have to differentiate the two. So sometimes you'll see ability to interact or ionize. If you shoot someone with an alpha particle, it's able to reach their DNA, it's going to do a lot of damage because it's so big, right? You can think of it as a rocket launcher here, right? A rocket launcher, you're going to have a tough time hitting something, right? But if it does hit, it's going to do a lot of damage. Now, if we compare that to a beta particle, it's more like a sniper rifle, right? It can pass through things a lot easier. It's a lot more accurate, but because it's smaller, it has less energy, it's going to do less damage than the rocket launcher, right? Same thing with gamma, right? Gamma's going to be precise, but it's not going to do as much damage. So if we're looking at ability to ionize, right, alpha has a super high ability to ionize. If you get it by DNA, it's gonna damage that DNA quite a bit because it's so big, right? And then if you do gamma, gamma's got a really low ability to ionize because it's probably just going to pass through things and not actually interact with it because it doesn't really have a charge. And then beta is somewhere in between, right? It has more of an ability to interact with it, so it could do some damage, but it's much smaller, less energy, so it's not going to do as much damage. So that's how we'd sort of rank things in terms of the ability to ionize. So you can see it's different than their penetrating ability. This video, we don't need to watch this video. It just talks about a gamma knife, which can be used to operate on brain tumors. So the reverse reaction of a beta decay can occur where a proton changes into a neutron. When a proton changes into a neutron, a positron is emitted, which is the antimatter equivalent of an electron, and we call it a beta positive. So every type of matter has an antimatter. It's kind of like an evil version of itself, if you want to think of it like that. So if we change a proton, mass of 1, charge of 1, and we change into a neutron, mass of 1, charge of 0, right? What we're going to be left with is something with no mass and a positive 1 charge, which is a positron. Okay, a positron has the same mass, same charge as a electron, but just the opposite charge, like opposite sign. It's still 1 elementary charge, but with no mass. Okay, so that's how we make a positron. So write a nuclear reaction for the positron emission of fluoride-19. So pause this, give it a go, see if you can do it. So fluorine, right, you can look that up. Fluorine is element number 9 here. So it would have 19 as its charge, 9. It wants to undergo a beta positive. Right, so plus 1 down here. So we're still going to be 19 up top, but on the bottom, it's going to be 8. 8 plus 1 is 9, so it's going to turn into oxygen, right? Number 8 is oxygen there, and that's how you do a beta positive. So with positrons, this brings into the idea of matter annihilation. So positrons, as with all antimatter, exist for only very brief periods of time. And this is because if you bring a positron nearby anything, well, that anything is going to have a lot of electrons, right? And it's going to be attracted to that electron. It's going to collide, and what they do is they annihilate one another. Annihilate is kind of a cool word that we don't get to use very often. So positrons soon come into contact with the electron, and both are annihilated. And when they annihilate each other, their masses are converted into pure energy according to E equals mc squared. And in the process, 2 photons of gamma radiation are produced. So this is our matter annihilation formula here, right? A beta positive, beta negative, and they make 2 gammas. But why do they make 2 gammas? So consider that E positive, E negative come in together with equal speeds, collide head on. Why would momentum not be conserved if only 1 photon was produced, right? Well, so we have our E negative, we have our E positive. They come together head on, so they have the same mass, they have the same speed, but with opposite directions. So to find our total momentum, it would just be the momentum of our E negative plus the momentum of our E positive. Well, it would just be mass times velocity of this, mass times velocity of this, but this would have a negative velocity. So what's our total momentum going to equal? Well, it's going to equal 0. If we just shot off 1 gamma photon like that, well, we can calculate momentum as h over lambda, right? So this has momentum. And if we just shot off 1 this way, we would have whatever this momentum is. So our momentum would go from 0 total to having momentum. That doesn't make any sense. So we need to shoot off another 1 to cancel it out so that our momentum after is 0 as well. So we always need to make 2 because it follows the law of conservation of momentum. So pairs production is the opposite. So the reverse reaction can occur when a high energy photon, gamma, or X-ray collides with matter to produce an electron-positron pair. So in this pairs production, the energy is converted to mass again by Einstein's equation. So it's just the opposite of the last equation that we had there. So a positron and an electron are traveling at 7.89 times 10 to the 7 meters per second. Calculate the frequency of each photon created due to the collision of matter and antimatter. Okay. This is a tough question. So we have a positron, electron, they're traveling at that speed. So we need to think of all our energies, because energy and momentum are all conserved, right? So we're going to have EK of our positron. We're going to have EK of our electron. And you also have to remember that E equals mc squared. There's energy and mass. So we'll have the energy of the mass of our positron, and we'll have the energy of our mass of our electron. And we have to add all these energies together to figure out what the energy of our photons are going to be. It wants to know each photon. Okay, so this is going to be 1/2 mv squared plus 1/2 mv squared. And remember, there's no direction with energy. And this is E equals mc squared plus E equals, oops, I guess not E equals, but just mc squared. And I'm going to make life easier on myself because they have the same mass, they have the same speed. I can just take this, multiply it by 2, take this, multiply it by 2. So I'm going to plug that into my calculator. So I'm going to go 1/2 times the mass of an electron and a positron, they're the same one, 9.11 times 10 to the negative 31, times my speed, 7.89 times 10 to the 7 squared. So that's the kinetic energy of my positron. I'm going to multiply it by 2, and that's the kinetic energy of my positron and my electron, right? And then I have the E equals mc squared. So if I take the mass of my electron or my positron, same mass, and I multiply it by the speed of light squared, that's the energy that I get from my mass. So I'm going to multiply that by 2 because there's 2 of them, right? So this is the mass energy. This is my kinetic energy. So I need to add those together. So I'm going to take this. I'm going to take this. There we go. I'm going to add it to this. And this number here is the total amount of energy I have available to me. So this is 1.69 whatever times 10 to the negative 13 joules. That's how much energy that I have available to me. And then what I'm going to do is I'm going to make 2 photons with that. So I can take this energy and I can divide it by 2 because it's going to be split evenly between the 2 gamma photons that I make. So I'm going to take this and I'm going to divide it by 2. So this is how much energy each gamma photon is going to have. And I want to find the frequency, so I can finish this off with E equals HF. Put H down here. And I'm going to use the energy that I just calculated when I divided it by 2. And then this is going to be my 6.63 times 10 to the negative 34, because I'm in joules. So I'm going to take my answer. I'm going to divide it by 6.63. times 10 to the negative 34, and I get my photon to be 1.28 times 10 to the 20 hertz, which is right in that nice gamma range that we should get. So you have to include all the energies, and the reason that we make 2 is because law of conservation of momentum. So energy and momentum are really important with this. So the last thing we're going to talk about is neutrinos. So during the beta decays, beta positive, beta negative, the daughter nucleus has a lot more mass than the electron emitted, right? So if this was our parent, if this was our daughter, and we shoot off this beta, whether it's positive or negative, it's kind of like, I don't know, I'm just trying to think. it's kind of like an asteroid hitting the Earth, right? The Earth doesn't move when an asteroid hits it because, well, like not an asteroid, but like a meteor. There we go. When a meteor hits the Earth doesn't move very much because the Earth is such a bigger mass, right? So when this flies off at a super high speed, and because this is so much heavier, it basically doesn't move. Oops. So therefore, there's almost no recoil of the daughter nucleus because this is so much heavier than this. So scientists assume that all the kinetic energy released during a beta decay would go into that kinetic energy, that electron. Okay. When they calculated it, they found that most electrons have slightly less kinetic energy than predicted. So during beta decay, some energy was missing, which doesn't make any sense. So a famous physicist, cool named Wolfgang Pauli, suggested that this mass was carried away by an undiscovered neutral particle called a neutrino. This is what he predicted, and it kind of sounds like ether, like, ooh, there's this magical substance that is there, but he ended up being correct because they found it. They discovered neutrinos.
Neutrinos are tiny, almost weightless particles that only interact via gravity and nuclear decay. Because they don't interact electromagnetically, that is, with light, they literally can't be seen. In fact, detecting a neutrino is kind of like trying to catch a bullet with a butterfly net. A beam of neutrinos will travel through lead for 2 years before it stops. In comparison, radiation from nuclear fallout can be blocked by about 10 centimeters of lead. So how do you detect a neutrino? One common way is to fill a big tank with water. We know light slows down through water, and if a neutrino with enough energy happens to knock into an electron, the electron will zip through the water faster than the light does. When this happens, the electron gives off a weak glow called Cherenkov radiation. It's kind of like a sonic boom for light, and it allows us to detect the neutrino. The biggest neutrino detector in the world is a balloon over the South Pole that actually uses the whole Antarctic ice sheet as its tank of water. Neutrinos also tell us that the universe is not the same as its mirror image. If you switch left with right, clockwise with counterclockwise, almost all of physics, like gravity, electromagnetism, and the strong nuclear force, is unchanged. However, the weird thing about neutrinos is that in physics terms, they're all left-handed. Their mirror image doesn't exist, so neutrinos are the vampires of physics. This fall, physicists in Italy published results suggesting that neutrinos travel faster than light, significantly faster. If true, this is really big news in physics. And of course, most scientists are greeting the results with skepticism. Why, you might ask? Well, they fly in the face of the well-established and experimentally supported theories of special and general relativity. And extraordinary claims require extraordinary proof. So let's go visit the opera experiment in Italy and try to catch some neutrinos. The kind researchers looking for the Higgs boson at the LHC in Switzerland are already crashing protons into each other to create explosions of subatomic particles. And luckily, some of those particles are neutrinos, which fly straight through the Earth's crust to us here in Italy. There are just 3 things that we have to do. 1, we have to catch the neutrinos, which, given that neutrinos will travel for roughly 2 years through lead before stopping, is an ambitious task. But we can do it. 2, once we have a neutrino, we have to figure out which proton collision it came from. Imagine blowing up a case of wine bottles at night, and then having your neighbor call you up and say, "I caught a piece of glass, can you tell me which one it is?" Well, we're that neighbor. And 3, once we figure out which collision a neutrino came from, we have to know exactly what time the collision happened, and exactly when we caught the corresponding neutrino. And because the scientists in Switzerland are hundreds of kilometers away, we have to use timing signals from GPS satellites in order to synchronize our clocks. If we're off by even a microsecond, we'll get the speed wrong by 1,000,000 kilometers per hour. So that's it. Now that we've measured the neutrinos going faster than light, what next? Well, because our results are so groundbreaking, and our observations so hard to make, the scientific community wants to be absolutely sure we didn't make any big mistake. So we have to wait for other experiments around the world to confirm or refute our claim. And this could take months, or even years. So be patient. And in the meanwhile, why not learn more about neutrinos, or how GPS works? Click below to make a choice.
So those are some videos on neutrinos, how they found the neutrino. So neutrinos are so small that physicists have yet to determine their mass. They're called a ghost-like particle because they can pass through the Earth with very, very little chance of being absorbed. They're so tiny, they're neutral, right? In 1956, they did intense radiation tests at nuclear power plants. They showed neutrinos existed, and there are two types of neutrinos released during beta decays. So there are neutrinos, which are like a V, and antineutrinos, which are a V with a line over it. Antineutrinos are coupled with beta negative, and neutrinos are paired with beta positive. Okay, so I'll do an example of that. So here's a meme. Bad Luck Brian, he's an old one, but I like this one because you have to know a little bit about neutrinos. So get skin cancer from neutrino ionization. If you don't know Bad Luck Brian, like the worst possible, like the smallest possible chance of something happening always happens to him. So the chance of neutrino ionization, right? Neutrinos acting with matter, they can pass through the Earth and never interact. Well, Bad Luck Brian ends up getting cancer from neutrino ionizing with his DNA. No. So write the nuclear reaction for the positron emission when fluoride-19 isotope with the proper neutrino. So positron emission. So fluoride-19, we did this one already. It gives off a beta positive. And then the other one that it makes is oxygen. Right? So you need, this would be incorrect the way that it is because we also need to add on our neutrino. Okay, and you need to know, is it beta positive or beta negative? Which one is it? Well, the neutrino is with beta positive, right? That's what I said right here. Neutrinos are paired with positron emissions. So say if I did this with a beta negative, so that would turn into 10, which is neon, I think, and 19. And this would end up a beta negative, right? I remember that, so the negative here corresponds with the negative there, right? That's how I remember it. Okay, this is your homework. Give that a go. Enjoy.